Hi, my name is Mac Ernest, and I'll be doing the merry-go-round problem from Lon Kappa. So, we are sitting, or I guess a child is sitting, on a moose seat on the carousel. That's 8.3 meters from the center of the carousel. And we've been told that it goes around in a circle once every 9 seconds. So that we've been given our radius, 8.3, and we've been given our period, 9 seconds. The first thing that they want to know is the child's speed. Well, it'll be easier to find the speed if we get the acceleration, which is actually the next step. So we're doing the next step first. The acceleration formula for circular motion is a equals 4 pi squared times the radius over t squared, the period squared. We have our radius, 8.3, so from that center point all the way out to the moose is 8.3. And of course we have our acceleration vectors going to the center, and our velocity vectors tangent to the circular motion. And we have our period, 9 seconds, so we put our radius and our period into the formula for acceleration, and our acceleration of the child is 4.045 meters per second squared. Okay, and then we can check that by sort of plugging it in to the original equation and then leaving out our period. So our acceleration is 4.045, and set that equal to the chunk of the formula, 4 pi squared, and then times our radius, and then over our period squared. So we'll solve for the period to prove that 4.045 is a reasonable answer. So we multiply both sides by t squared, 4.05 t squared equals 4 pi squared 8.3. And then divide both sides by our acceleration, 4.045 meters per second squared, and we get take the square root of both sides, and then we get our period equals 9.00036, which we can all agree is pretty close to 9 seconds, which that period should be seconds. And then we want to find the child's speed. Now that we have acceleration, it's pretty easy to do that. So another formula of acceleration for circular motion is acceleration equals velocity squared over the radius. Now, if we do some manipulating, we get speed equals the square root of acceleration times the radius. And then we have our acceleration, which was 4.045, which we proved, and 8.3 is our given radius. Multiply those and take the square root, and that's 5.974 meters per second. So the child's speed on the moose is 5.974 meters per second. Now, they want to know what the acceleration will be when we move in a little bit. Like, so if the child were to move to another seat closer to the center of the carousel, so 5.9 meters away from the carousel, and we can assume that the period is the same because it's the same carousel, so it's still going to go around at the same length of time. So our acceleration equation is still the same, a equals 4 pi squared radius over period squared, which if we plug in our values for the radius and the period, we get 4 pi squared times 5.9 over 9 squared, and our acceleration at the different seat is 2.876 meters per second squared. And then to check that, we can just do it like we did earlier and try to solve for t, our period, instead with the acceleration answer that we got. So I went ahead and manipulated the equation to get the period by itself, and then you take the square root of both sides, and the period equals 8.99936, which we can all agree is fairly close and reasonably close enough to be 9. So our answer should be correct.